Hello everyone, this is Ankur and I'll be presenting our work on benchmarking humans and AIs on the many facets of working memory. This is a joint work with Mengmi Zhang from A-Star and NTU Singapore. Working memory is a limited capacity memory system in humans which is used to temporarily store and manipulate information to support cognitive tasks. We argue that a similar model of working memory will be crucial for future AI models to support tasks that involve reasoning, decision making, planning, and more. And there have been numerous studies in neuroscience and cognitive science to investigate human working memory. However, there is a lack of a comprehensive and large-scale working memory dataset or a framework which researchers can use to study modern AI models and humans together. In our work, we propose a new dataset called WORM to benchmark humans and AI models on a carefully chosen set of working memory tasks. We classify these tasks into 4 categories based on the different functions of working memory, namely storage, integration, manipulation, and task supervision. Examples of few tasks under storage function includes visual serial recall and change detection. For memory integration, we include tasks like spatial coordination and spatial integration. For memory manipulation function, we include a task called spatial memory updating. And finally, for supervision, we include a task called spatial task switching. Moreover, all these tasks span across 3 different domains of working memory. Therefore, models are required to capture visual, spatial, as well as temporal information about the presented stimulus. Our dataset contains around 1 million trials distributed across training, validation, and testing splits, and spans over 4 different functions and 3 different domains of working memory. Finally, we benchmarked multiple computational models on 11 different working memory characteristics like primacy and recency, effects of set size, task selectivity, and more. For our computational model, we considered a joint training paradigm where we train our models jointly on all the working memory tasks. First of all, raw images from trials belonging to different tasks are batched together. This batch of raw images is then fed to a CNN model for feature extraction. Note that the CNN model used here is shared across time steps. After feature extraction, the representations are then fed to a working memory model. In our work, we conducted experiments with contemporary memory architectures like RNNs, GRUs, LSTMs, and transformers as the working memory model. Finally, the output of this model is then passed to different task-specific linear classifiers that output the predictions of the model for given tasks. Here I will briefly describe one of our tasks called Visual Serial Recall task. In this task, the trial begins with the presentation phase, during which unique visual patterns are presented at different time steps. The models are required to remember the visual pattern as well as the temporal order of the patterns. This presentation phase is followed by a probing phase where all patterns are presented simultaneously. During the probing phase, the models are required to predict the patterns in the same temporal order as was presented during the presentation phase. This task basically involves the memory storage function and is operating in both the visual domain and the temporal domain. Here we define list length as the total number of stimulus presented during the presentation phase. So in this case, the list length would be 4. So basically, longer the list length, higher is the memory load for that particular trial. On this particular task, we evaluated our computational models, and in this plot, we compare a LSTM model and human performance on the task. On the x-axis, we show the serial position of a pattern, and on the y-axis, we show the recall accuracy. We observe that recurrent models like LSTMs show primacy recency effects very similar to humans, where the recall accuracy for the initial and final items of the list is higher than the recall accuracy of the intermediate items. Moreover, this effect is stronger with longer list lengths where the memory load is higher and is weaker for smaller list lengths. Note that these computational models were neither trained or fine-tuned on any human data. Moreover, we also studied the effect of retention intervals, set sizes, memory resolution, task selectivity, and more. Please refer to our paper for more details on these experiments. In conclusion, we propose a large-scale and comprehensive benchmark dataset for working memory. We establish a general methodology to jointly train and evaluate computational models on working memory tasks. Moreover, we compare AI models and humans on multiple behavioral benchmarks and conduct extensive neural population analysis for the trained models. Thank you for listening.